matrix representation of scalar product. So matrix is a very useful way of computing the linear algebra. And actually, linear algebra is a kind of matrix algebra that originates from Cartesian coordinates. So it is very convenient to deal with a vector in terms of Cartesian basis vector, and that is called E1 hat, E2 hat, E3 hat. And because they are linearly independent, the components are uniquely defined. So that is the reason why we use basis vector, because the coordinates are uniquely defined. In addition, even though there are many ways to select basis vectors that are linearly independent, it is very, very convenient if we choose each vector, each basis vector to be of magnitude unity. So E2 squared, 1, E3 squared is 1. In addition, it is convenient to choose the three vectors that do not overlap. That means no parallel component exists. That means everything is orthogonal. They have a right angle because the scalar product is a 1 times 1 times cosine, and the cosine is a half of pi. It is assumed to be 0. So 1, 2, 2, 3, and 3, 1, all of the Cartesian basis vector are chosen to be orthogonal. In that case, it is very convenient to express the scalar product if we introduce a matrix form. Before we go ahead with dealing with the scalar product, we just define the column vector. This is a column vector, and this is a row vector, row, column. And the multiplication of a row vector and column vector is defined only if the number of elements are the same. We are working on a vector in 3 dimensions. We have 3 coordinates, so these are 3. So basis vector appears in the column, and components appears in the row, and we know every index 1, 1, 2, 2, and 3, 3. They are the same. That means multiplication is defined by multiplying the first, second, and third pairs and multiply them and then add them all together. This is the multiplication of a row vector and column vector. By introducing this matrix representation, we can conveniently express a vector as a product of row vector and column vector. Because they are commutative, I can write it A1, E1 hat, and the E1 hat, A1. So this expression is identical to the left one. Okay. In some case, we just neglect this part and assume this column vector that contains the Cartesian coordinates only. We say this column vector is called a matrix representation of a vector. Then actually they are not equal, but there is an assumption. We have components. There is a hidden basis, E1 hat, E2 hat, and E3 hat are assumed to be hidden. In addition, if we want to define the scalar product with the 2 vectors using this matrix representation, it is convenient to convert a column vector into a row vector, or row vector into column. That is called the transpose. Transpose, usually denoted by capital T, and if I have a column vector and put capital T on it, and the result is a row vector. The order is the same, but this column is transformed into a row. Or I can attach 1, 2, 3, and I can attach a capital T here. This is transpose. This converts this row vector into a column vector. Okay. So we know how to compute the scalar product. Scalar product A dot B is A1 E1 hat, A2 E2 hat, A3 E3 hat, dot B1 E1 hat plus B2 E2 hat, and B3 E3 hat. We know the multiplication table for the basis vectors EI dot EJ. It is canonical delta IJ. That means it is a 1 if I equals a j, and it is a 0 if I is not equal to j. Therefore, using this multiplication table, I know the result is A1, B1, A2, B2, and A3, B3. Now I notice that it can be expressed in terms of row vector, column vector multiplication. So A1, B1, A2, B2, A3, B3. So the matrix representation of a vector is very, very convenient if we make use of a Cartesian coordinate system. So the father of this matrix should be Descartes. Okay, so we should be very thankful to Descartes for introducing this algebraic way of dealing with geometric problems. As you know, these multiplication of scalars are commutative, so I can replace the order. So this one should be this. So in the matrix form of this scalar product of two vectors can be thought as A transpose capital B, and A is A1, A2, A3, B equals B1, B2, B3 Cartesian coordinates. Or this should be the same, okay? They are commutative. Why don't we consider a very interesting matrix whose elements are scalar products of two sets of Cartesian unit vectors. Usually, they represent the rotation of a coordinate system. In physics, we prefer active coordinate, active transformation that changes the vector itself. However, in mathematics, they are more interested in changing the basis. What I mean is the vector is invariant and only the coordinate transformation is given. But mathematics deals with numbers that is not living. In physics, if you drive a car, the car is moving. So we are more interested in the changing something. So if you compute the velocity, you need to consider the position that depends on time, that changes as a function. something like that. So if in the rotation, we are more interested in active transformation, but in here, don't, we just forget about the passive and active, but just introduce two coordinate basis vectors. And we can compute the scalar product. In each set, they must be orthogonal, so they must satisfy this Kronecker delta. In the prime system too. So for example, E1, E2, E3, and we have another basis, E1 prime, E2 prime, E3 prime. So we would like to compute the scalar product between these unprimed and primed one, these and these, and so on. So 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. Okay. So why don't we compute we just multiply these coordinates that represents A1, E1 hat, A2, E2 hat, plus A3, E3 hat. We would like to express this vector in terms of something else with different bases. Then I'd like to keep the vector the same, so it is a passive. The vector is invariant, but I'd like to change the basis, then coordinates will change correspondingly. Okay, so we are interested in the transformation rule to find these primed coordinates in the new basis. So that is hidden in this expression. That's the reason why I call this matrix R represent the rotation matrix. Okay, let's see. We multiply this one in here, this one in here, and this one in here. So, and sum them all. I copied this and attach it A1, copied this and attach it A2, copied this and attach it A3 in a similar manner. I can see, aha, aha, aha. And this guy is E1 prime, E1 prime, E1. Everything is the same. They are factorized. So I can factor this one E1 prime out, and what I find is this kind of expression. This is E1, this is E2, and this is E3. Okay, and what's that? This one can be replaced with A1 is actually E1 dot A vector, right? How to find a component is I just multiply the unit vector to find the component. So A1 is replaced with E1 dot A, E2 dot A, E3 dot A. Okay. So finally, what I find is it is multiplied with E1 prime and E2 prime, E3 prime. What's that? This is nothing but the A vector itself. You know the completeness relation. A vector is decomposed into three pieces, and each component, this one is E1.A, this one is E2.A, and this is E3.A. So this is a completeness relation. Sum of the all three components will give the same value as the original vector. As a result, this is E1 prime dot vector, E2 prime dot vector, E3 prime dot vector. Oh, what's that? This is the component in the new coordinate system, primed coordinate system. So this one should be replaced with A1 prime, A2 prime, A3 prime. Finally, these primed coordinates are obtained by multiplying this rotation matrix that is composed of directional cosines the scalar products with the two basis vectors, okay, if I know the original coordinates and if I know the directional cosines as a matrix form, just multiply, then I will find the Cartesian components with the new basis vectors. Okay, so what we conclude is this. Explain the completeness relation within passive transformation by making use of the result of A. Using this result of A, the completeness relation is written in this form. So Cartesian component along the x-axis is E1 dot A, y-axis is E2 dot A, E3 dot A. So take the scalar product and multiply that unit vector and sum them all for all linearly independent directions, then you will find the original vector. And that is true for the new coordinate system too. So because both E1, E2, E3, and E1 prime, E2 prime, and E3 prime, these two sets of bases represent a single vector without missing anything. So this completeness relation is true in any coordinate system as long as your basis vector do not miss any vector. So base is a very useful idea.